Let's take a look at the switch. This is out of a hydraulic power pack. It's a momentary switch, so it would normally be underneath these buttons right here. And conveniently enough, when we take it apart, it's clear, so we can see what's going on. So momentary, as in we push it down for a moment, let go. The circuit is now disconnected, and that gets us to the point we're talking about today, which is the difference between a normally open and a normally closed switch. So this is a normally open switch. We can actually see through these little doors right here. There's a brass contact or copper contact on the top there, and then another one down below right here and right here. A side profile view of that same thing is right here. So upper contact, lower contact. Now, when we move the button down, our upper contacts make contact with the lower on both sides. And each of these two circuits, so this is a two-circuit switch, each one operates on the ends. So this is split from this way and this way. And right now, when we have the button released, which is its normal condition of a switch is hand off of it, switch out of application, what is the electrical state? And so right now, if we hook up our meter lead, we can see what the electrical state is of this by just hooking up our meter. There we go. So we hooked up our meter positive, negative. We have our multimeter on ohms, and we have our meter auto ranging. Auto ranging is helpful when doing switches because you will go from out of limits, infinite resistance, millions of ohms essentially, but beyond measurable for your meter, that's an air gap resistance, all the way to 0 ohms, which is perfect continuity, which is what we'd expect when we operate the switch. So this is a normally open switch, so we have an air gap between the contacts. We would expect OL. Some of your meters will say OFL. When we press the button, we expect those copper contacts to make contact, and we would expect our resistance value to go down. Now, we would like it to be even lower than it's showing. So right now it's showing at 0.3 to 0.5 ohms. And so a little bit of that is, we're going to figure out whether that's in my attachment of the leads. There we go. Or it's also possible, because this was an in-service switch, that it is corrosion, oxidization, or erosion from arcing at the contacts of the switch. And that is ultimately what we're looking to test. When you're working with a switch that's not working properly, sometimes you feel like you have to push it a few times before it finally works. What you're doing is rubbing through the arcing or the oxidization on those contacts to finally get them to work. And you can see that as I bump it around now, I'm down to 0.1 ohms, which is what I'd expect to see. And so that means when we release it, we are open, OL. When we close the contacts, we are down to 0.3, which is a closed switch. So this is a normally open momentary switch. But more than that, this is what we would call a dual pole or double pole or two-pole switch. Now, poles go to the number of circuits in the diagram. Or when you look at your wiring diagram, if you saw two dots and you had two separate wires being controlled by the switch, that's what would be going on right here. So this has one circuit here and one circuit here being controlled. And when you push the one button, both circuits are complete. And we have isolation from one circuit to another. And that's something you'll also want to make sure you check when you're working with multi-pole circuits, is that you don't have a short happening inside, that we have a wire-to-wire short happening. So even when I push the button or not push the button, we don't have continuity from terminal to terminal across this switch, and that is what we would expect. So I would expect there to be continuity here when we push the button, continuity here when we push the button, and opens when we don't push the button. And so this is a double pole, and now we would call it a single throw switch. And what the throw is how many electrical positions there are. So we can just see from this side, there is only one electrical position. We either make a contact or we don't. There is no extra contact, so I'll push this down and you'll see that movement. There is no extra contact above this plate. All right, so there's not an either or position. It's either powered or it's not. That's the only either or. It's not like a relay. If you go to a 5-pin relay, like this one here, you have an 87 and an 87A, which is the either or electrical position. So it's either electrically powered here or here, but there is no middle. This one only has one position electrically powered, the other one simply isn't. And so in that way, it looks much more schematically like this diagram right here, where you have a dot, so that's the pole, the circuit that's being controlled, and it's either complete, connected to this dot, or it's not, much like this. So this is actually a single pole, single throw switch drawn, and that is what one side of this is, and we actually have two of them together in the circuit. So this is a dual pole, single throw, momentary switch that's normally open. Now, why we need to know that is that's what we're going to do with testing. We are going to test, is there continuity between these terminals released? If there is, it's shorted. If there isn't, if it's OL, then that's what we'd expect. But now also close it. When we hit the button, does the contacts close? Do we actually have continuity from terminal to terminal? And if we don't, if we have a high resistance, really this should be very close to zero, like almost on zero, so 0.1, because my meter's base resistance is 0.1 on my leads right now. So 0.1 reading, that's good. But if we consistently got 8 ohms here, that 8 ohms would be creating an unwanted resistance in this switch, which will create a voltage drop. And in our electrical circuits, any voltage drop in a circuit is a loss unless it's our desired load. And what'll actually happen is it'll start to generate heat in the switch, and it'll actually start to melt these plastic switch bodies. And that's one of the reasons why our switches are rated to a voltage and an amperage, is they can only handle so much heat before they start to melt. So we need to know what the switch is so we can know how to test it. And then once we test it, we need to know what those results actually mean.